Sorry, there's some slightly elaborate setup. Sorry, there's some slightly elaborate setup. Thanks for coming in so early in the morning, and thanks for the opportunity to speak here. It's a pleasure to continue the nice talks yesterday on extended formulations. So let me just begin by recalling what was sort of the main conceptual lemmas and theorems that we saw yesterday. And the most important thing was we're looking at this concept of extension complexity, which is given a polytope. What is the smallest size linear program, or a polytope with the smallest number of faces, of which this is a projection. And this is characterized by, so we have a polytope P, and we want to understand what is the smallest polytope that of whose P is a projection. Surprisingly, this is characterized by an object which is completely well defined given the polytope P, and the object is a slack matrix. The slack matrix is a matrix where you have one column for every vertex and one row for every face, and the entry S of f comma v is the distance of vertex v from the face f. And the theorem of Yannakakis, which is the main underlying theorem on all the results in extension complexity, is that the extension complexity of a polytope P is exactly equal to the non-negative rank of this slack matrix associated with the polytope. So just so we are all on the same page, the non-negative rank of a matrix, so we have given the slack matrix, the non-negative rank of the matrix is the smallest R, such that the matrix admits a factorization like this, like a long skinny matrix and a thin matrix, like so, where S is equal to U times V, and typically if you just minimize R such that S is equal to U times V, you get the rank of the matrix. Here we enforce an additional condition that the matrices U and V are non-negative. So, and that gives us the non-negative rank, and clearly non-negative rank is more than the rank. Okay, and the Yannakakis theorem shows that extension complexity of the polytope is the same as a non-negative rank. Okay, so hope it was clear so far. Okay, so one thing that Thomas alluded to yesterday at the end, and which is interesting, is that if you look at the slack matrix, we've defined it with one column for every vertex and one row for every face. You could, extend it further by having a vertex column for every point x in the polytope. So now it's an infinite matrix. And having one row for every hyperplane, or every inequality that is true for the polytope, every hyperplane which doesn't cut the polytope. So now it's an infinite matrix, but that doesn't change the non-negative rank of the matrix. It's just a different object, but it's sort of it will be useful to think of in these terms soon. And it was useful even in the lower bounds, which Thomas showed yesterday, in that we use hyperplanes which are not necessarily the faces of the polytope. Okay, so even we, as an example, we'll restrict our attention to the correlation polytope. So what's the correlation polytope? It's the convex hull of XX transpose, where X is a Boolean vector. Okay, and why is this polytope interesting? The reason it's very useful is that if you want to optimize any quadratic function over the Boolean hypercube, that's the same as optimizing a linear function over the correlation polytope. And a lot of combinatorial optimization problems can be posed as optimizing a quadratic function over the hypercube. So in particular, if you look at the max cut problem, you're given a graph G. The max cut problem is you're just trying to maximize the number of edges cut, and if LG is the Laplacian of the graph, then maximizing the number of edges cut is essentially maximizing this quadratic form, x transpose LGX, over the Boolean hypercube, and that's essentially the same as maximizing a certain linear function over the correlation polytope. So there are a lot of NP-hard combinatorial optimization problems can be solved if you could express correlation polytope compactly. And so it's a very useful, important polytope to study. So another thing is I wanted to mention is yesterday we went faster than we expected. So I have more time than we expected today. So so please ask questions. Stop me whenever I'm not clear. A lot more time, and we might end up stopping early. Okay. So now we have this correlation polytope. So I think it's a good idea to actually go back and look at the slack matrix and non-negative rank in terms of the problem that we are solving, which is the max cut problem, instead of the polytope. So it's the same thing, but it's just somehow I find the terminology might be useful to think about these things. So we're trying to solve this problem max cut, which is this maximization problem. And that's the reason we looked at this correlation polytope, which is a convex hull of XX transpose, which are the solutions to that problem. So now, if you look at the slack matrix, right, so what are the vertices? The vertices are nothing but, these are nothing but integer solutions to the problem. These are the integer solutions for the problem that we are studying. So in this case, if it's a max cut problem, it's just say one column for every integer solution. And for the faces, well, in general, we have every face of the correlation polytope, but really the faces that we care about are the functions that we want to optimize over this polytope, which are just really the graphs, the max cut graphs. So the faces really correspond to instances of the problem. So in this case, if it's max cut, it's a bunch of graphs, and if it's some other problem, it's all possible instances. So you could define this slack matrix not for a polytope, but for a problem, where you sort of have integer solutions and as your columns, and your rows are all possible instances. Again, it's an infinite matrix, and the entry is just the upper bound that you want to certify on that instance. So the entry, like for instance in max cut, what is this S of G comma X? Maybe you want to certify an upper bound of C. So let's say C, or let's say you want to get an alpha approximation. So you want to certify an upper bound of alpha times opt of G minus X transpose L sub G X. Right, so this is if you look at this function, what you really want to do is to certify non-negativity of that function. Okay, actually I went a little bit ahead of myself. So if you essentially, now that you have this idea that the rows are integer solutions, the columns are instances, any row of the matrix is just a function on solutions, a real valued function on solutions, right? Clearly, just because it's a column vector, it's a vector with that many entries. So it's a non-negative function on solutions.
So Prasad,
yes.
Can you explain again why the faces are instances?
Why the faces are instances? Yeah. So actually, not every face is an instance, but I should be more precise. I should say every instance is a face, in the sense that Right, so what are we trying to do? We're trying to solve max cut. So we wrote this optimization over the correlation polytope, right? So, and what does it mean to certify the value of the max cut being smaller than, let's say, C? It's just to certify that C minus L sub G comma X is greater than or equal to 0 for all X in the correlation polytope. Okay, this is true. This is what we're trying to certify. So this is a hyperplane that we want that separate. That's on one side of the correlation polytope. So that's an inequality. So so therefore, essentially every row is an instance. Or actually, the only rows that we care about are instances of max cut. Because if you're trying to solve only max cut and not care about the correlation polytope, the only rows of the matrix that we care about are instances of max cut. And the only columns we care about are the integer solutions. And the entry, suppose you want to get an alpha approximation, is just alpha times the optimums on that graph minus the value of the cut x on the graph G. So that's the function, which is this row. Suppose I look at the row corresponding to a graph G. This row is actually equal to this. Okay.
So you're just adding redundant constraint, one for every graph.
Yeah, we just So essentially, we are going and so you can define a slack matrix for a problem and things like that. But the construction is essentially the same. Okay, does it make sense? And then you could talk about extension complexity of a problem, saying what is the extension complexity of getting an alpha approximation for max cut? That's equal to the non-negative rank of this matrix. Okay, so
alpha is less than 1. Do you need to truncate it to 0? It could be
right. So actually, alpha is some fixed number more than 1. Right. So here alpha, there's no this in some sense alpha is some fixed number more than 1. Suppose you want to understand what is the extension complexity of getting a 1.1 or 1 over 1.1 approximation for max cut, then you're trying to certify that the value of max cut on a graph G is not 1. You're trying to certify an upper bound on the value of max cut. Yes.
Just to be clear, so this kind of instance and vertex viewing is only for the correlation polytope.
So the question was, is this kind of instance versus solution way of looking at slack matrix, is it only for the correlation polytope? No, it's essentially for every problem. For every problem. I mean, every problem where extension complexity sort of applies. Extension complexity doesn't apply to problem, or it's not very cleanly applicable to some problems. Like for instance, if you look at independent set problem on a graph, the extension complexity, it's a little bit tricky to define extension complexity there, because in terms of writing LPs, extension complexity is sort of a lower bounds against LPs whose constraints do not depend on the instance. So if you write an LP for max cut where the constraints of the linear program do not depend on the graph, just like what we're doing here, the correlation polytope is independent of the graph. Lower bounds for extension complexity are like that. And that's mostly what we can do for many problems, so it's interesting. But if you look at a problem like independent set, it makes sense to add a constraint for every edge. Or for 3SAT, if you look at a clause, you want to add a constraint for every clause. And therefore, it doesn't it's a bit tricky to define extension complexity carefully there. But yes.
It would work for weighted independent set.
Yes, it would work for weighted independent set, where you fix the edges, so you allow the person to. And in fact, there is a nice lower bound by Swenson and Pokuta which actually they prove an extension complexity lower bound in the following model. I'll show you a graph. You can look at the edges and write arbitrary constraints, but then I will reveal the weights on the vertices with respect to which you want to solve minimum vertex cover. And then the extension complex, they get a, I think I think was it exponential lower bound? Yeah, they get definitely a super polynomial lower bound for this in this word, but it's a little bit subtle to define it. Yeah. Yes. You had a question.
Wait, couldn't you still define a polytope where, as well as just writing down the independent set itself, you also write down, like for all pairs of vertices, are both of these in the set or something like that?
Yes. So.
And you would be, I guess that would at least give you, if that had low extension fluxes, that would at least give you a positive result.
Yes. Yeah. So that's right. So you can sort of pose independent set. For instance, you can write maximum independent set as a linear function over the correlation polytope. You can do it, and therefore, but when we're trying, but essentially lower bounds for extension complexity make a lot more sense when there's no reason the linear program has to depend on the instance, and it becomes more and more tricky as it, as you add constraints that depend on the instance. Okay, so any questions? Okay, so let's. So now with this viewpoint, if you look at what's happening over here in the slack matrix, right? Every row of this is again a function over solutions, and non-negative function over solutions. Okay, the row Vi is a non-negative function over solutions, and what we are trying to do is, if we have a small number of these functions, there are R rows, there are R different functions, and what we're trying to do is to express the function that we want to certify is non-negative as a non-negative combination of these. So let me be, I'm going to write it up. So basically, using this, the way we described it, every linear program for max cut or of size R, or I could even say every extension, every extended formulation of correlation polytope corresponds to a family of functions on the hypercube. Okay, if you have a linear program with R constraints, there are R different functions on the hypercube. Okay, and so if you think of it in terms of proof system, you want to think of these as your axioms of your proof system. These are the axioms that the linear program knows to be true or non-negative. And the theorem is that the LP, let's say if you are talking about approximation, let's say the LP yields an alpha approximation if and only if for every graph, if you look at the slack function for that graph, what is the slack function for that graph? It's again a function on solutions, which is alpha times opt of G minus X transpose, the value of the cut. This function, there's a Boolean function, is a function on the hypercube. This should be a non-negative combination of the family F. So it should belong to the cone F. Okay. Alternately, the linear program certifies that this function is non-negative by writing it as a non-negative combination of the axioms it knows. Okay, and the most obvious example is what happens for, let's say, the D round Shirley-Adams. For D round Shirley-Adams, the family of functions is just non-negative D juntas. Where a D junta is a function that depends only on D coordinates. Okay, so these are functions F such that F depends on X sub S, where S is at most D. Okay, so if you look at non-negative D juntas, this is a family of functions, and if you use this family of functions, the LP you get is the Shirley-Adams LP. So you could equivalently define Shirley-Adams LP in terms of this family of functions. Okay, and so the reason we are able to prove lower bounds in extended formulation is sort of this very simple setup, where in some sense when you're writing down an LP, you're trying to pick the axioms. You're trying to pick a small number of functions, okay? Because the number of functions is the size of the LP. And once you pick the small number of functions, you're supposed to be able to write every slack function as a non-negative combination of that. And so that's the reason we are able to prove lower bounds. So that's sort of what happens. So we say, oh, if you only pick R functions, you're not there are graphs which you can't write as combination, and therefore. Okay, so sort of the same thing is true with SDP extension complexity. I'll just state it. So if you want an SDP for max cut, if you want to talk about SDP extension complexity for max cut, an SDP of size R for max cut corresponds to having a vector space of functions. Like I've written down the basis, so there's a vector space of R squared functions. Okay, and such that SDP yields an alpha approximation if and only if the slack can be expressed as sum of squares of functions from that vector space. So in particular, in case of if you look at the example, which is the degree D SOS, the vector space of functions is this is just span of all, this is just low degree polynomials, degree D polynomials. Okay. And what the SDP does, is essentially given the slack function, it tries to express it as a sum of squares of functions from this vector space, which is sum of squares of low degree polynomials, or in case of if it's a general vector space, sum of squares of functions from that vector space. Okay, so this was some of this. A lot of it was already covered yesterday by Hamza. Okay, so now we want to prove lower bounds for extended formulations. But before we try to get to general extended formulations, there's an interesting subclass of extended formulations that we want to look at, which is symmetric extended formulations. So what is symmetric extended formulations? Here, you see that the correlation polytope has a lot of symmetries. In particular, I can permute the n coordinates of x. The correlation polytope stays the same. Alternately, the computational problem max cut has a lot of symmetries in the sense that permuting the vertices of a graph gives you another instance of max cut, right? So you might hope that the linear program that you write for max cut also respects these symmetries. So like at a very rough level, you might say permuting the vertices here I mean permuting the nodes of the graph, the nodes, not the vertices of the polytope, permuting the nodes of the graph might just permute the constraints in your LP. Okay. This is a natural notion of symmetry in the sense that the feasible region stays the same if you permute the nodes of the graph. But of course, this is a fairly, the way I've defined it, it's a fairly rough definition of what symmetry is. It's a little bit more subtle to define symmetry correctly for this. There are a few different definitions, or there are a couple of different definitions. One definition is to say, so you have the permutation group acting on the correlation polytope. Okay, yeah, for every permutation acts on the correlation polytope. What you would want to do is you'd want a lift map L that sort of commutes with the permutation, commutes with the action. So there's a permutation group acting on the correlation polytope. You want a corresponding action on the upper polytope, and then what you'd want is that the action commutes. Oops, sorry. Okay, so while my Apple Pen is charging, I will just put this right here. So it should take a minute maybe, but so I won't. Maybe I shouldn't try to define symmetry too precisely, but essentially what you want is this lifting map to satisfy this property, that if I lift sigma of x, that should be the same as taking the lift and acting acting upstairs. But you know, if you like, if this was not very precise, you could just stick to this definition, which is fairly intuitive and which is sort of true for all the polytopes that we know about. For instance, if you think about Sherali-Adams polytope, that's the canonical symmetric LP relaxation. In the case of Sherali-Adams relaxation for this correlation polytope, what would permuting the vertices, you're permuting 1 through n, the original variables, right? So that would permute pairs xi xj to some other pair, and so you would permute all the constraints of the linear program. So the faces, you get to permute the faces. Okay. Okay. So if this is true, then you could ask, what does it mean for the non-negative factorization? So now we want to prove lower bounds for just symmetric extended formulations. For symmetric linear programs for correlation polytope, what does it mean for the non-negative factorization? Okay, yeah, good. So, but before we get there, let's see what's known for symmetric extended formulations. The first results by Yannakakis was for symmetric extended formulations. Yannakakis showed that every symmetric extended formulation for the matching polytope or the TSP polytope requires exponential size. This is already very nice, and in fact, you might suspect that since a problem like TSP is so symmetric, or a problem like matching is very symmetric, there's no use in using an asymmetric relaxation for a symmetric problem, right? You might suspect that asymmetric relaxations are no stronger than symmetric relaxations for whenever the polytope is so nicely symmetric. But that turns out to be false, and that's a very surprising result by Kaibel, Pashkovich, and Thies, that if you look at the polytope of log n partial matchings, it has polynomial size asymmetric lifts, but no polynomial size symmetric lifts. Just a partial matching with log n edges, less than log n edges. And in fact, so going back to yesterday's talk, it could be that the extended formulation that we get by dynamic programming for knapsack is an asymmetric extended formulation, which is smaller than every symmetric extended formulation for knapsack. So asymmetry does help, and you can make in dynamic programs. It's very clear that you would want asymmetry. You would want to fix one variable, and you want to fix the order in which you'll do it. But this is what it shows.
But knapsack is not symmetric. I mean,
but the polytope is symmetric, right? So even over here, all matching instances are not symmetric, but the polytope itself is. So the knapsack.
If you have different types.
Oh yes, sorry. Yes. I'm sorry. Yeah, you're right. Yeah, actually, knapsack is not symmetric, so this doesn't even apply there. Yes. Okay. So. If my Apple Pen is charged now, let me see. Okay, so now we had this equivalence between LPs and family of functions, SDPs and vector space of functions. Let's see what happens here. If I write symmetric LP here, every symmetric LP corresponds to an invariant family of functions, and every symmetric SDP corresponds to a vector space with an invariant basis of functions. So what is an invariant family? So invariant is essentially the family stays the same if you permute. So what that means is, if you take a function from the family, okay, and then the entire orbit under permuting the inputs also is inside the family. So if you take any function in the family and you take any permutation sigma, this is a permutation. If I look at f composed with sigma, this is a new function. Okay. This function should also be in the family. Okay, so that's what it means for it to be invariant. So, like for instance, the family of all D juntas is invariant, because if you take a D junta and permute the variables, you get a different D junta. Okay? Not every function is invariant on its own, but the entire family stays the same when you apply this. This, as it turns out, is a very strong restriction on the family. Okay? And so you could ask, when can an invariant family be small? Right? We're interested in small linear programs or small like extended formulations. When can a symmetric extended formulation be small? Meaning, when can an invariant family be small? Let's try it out. So imagine you had a function. Suppose you had f of x is equal to, let's say, some majority on some n/2 coordinates. Okay. If you include this function in the family, then you would have to include every permutation of that, which will mean that you'll have to include every majority on every subset of n/2 bits, which means you'll have n choose n/2 different functions in your family. If f belongs to the family, then already it implies that the size of the family is super large. It's like n choose n/2. Okay, so there are very few functions that you can actually include and still, have a small size. So for instance, one obvious candidate is you could include f of x equal to x1 and x2, right? All permutations of this will give you n squared different functions, and that's fine, right? So in particular, you could include f is any D junta. This will give you, after permutation, at most n choose D different functions. Okay, this is one candidate. Okay, is there anything else that we can include?
We can depend on every variable symmetrically, like the sum of them should be symmetric.
Yes, so symmetric functions. So like you could include f of x is equal to summation xi, for instance. This is a function, and of course it's completely depends on every variable, but it's still, so every symmetric function is fine.
Prasad, when you say D junta, meaning if it's only n choose, I thought it was just only dependent on D variables.
Yes.
But there could be any function of the D variables.
Yes. Yeah, that's right. So a D junta on its own will generate n choose D different functions. So there are n choose D functions in the orbit of f, which is sort of acceptable because we have thinking of as LP of size roughly n choose D. But if you have size exactly n choose D, then you can have only one such function. Yeah. So
if it's a function depending on n variables that's symmetric, it's a function depending on the sum, because there's 0, 1.
Yes, that's a good point. So since we are a Boolean hypercube, if you have any symmetric function, it's a function of summation xi. Any symmetric function is essentially h of summation xi. Okay, and you could do something slightly more complicated. You could mix the two. Basically, you can have f of x to be a function of some subset of D coordinates and the sum of all the coordinates. Okay. If you look at such a function, this will also generate n choose d. And as it turns out, this is essentially all you can do, right? If you take any Boolean function any function in the hypercube whose orbit is at most n choose k, it's actually a function of the form h of x sub j comma summation xi, where j is at most k coordinates and summation xi is the sum. It only depends on the sum and the and k coordinates. Yes.
So why can't we use n minus d quantas?
That's a combination.
Right. Yeah.
Right. So why couldn't we use n minus d juntas?
Intra-junta permutations. So the same junta, but you permute the variable inside.
Right. Yes. Yeah. Yes. Right. The issue is really when we permute the variables, you also you could generate new functions that way. For instance, if you had a crazy function on n minus d variables, when you permute the variables inside, that function itself will generate new. So your function on n minus d variables will also have to be symmetric somehow, right? Basically because if we take, yeah, did that make sense? So if for instance, if you had some function, some asymmetric function on n minus d variables, h is an asymmetric function on n minus d variables, then if you permute all the variables of x, even though you're using the same set of n minus d variables, you will still generate new functions that way. So it's a very strong symmetry to say that the orbit is small. Yeah.
But what if, I mean, wait, sorry, I'm confused now. So what if I want to take the end of all but one variable? So there's only n of these.
Oh, and of all but one variable is a function of this type. Because if you knew the sum of every bit, and then if you knew that bit, then you know and of every, yeah. Okay, so how much time? Okay.
So what's on that? Also, I don't see the difference between d and n minus d. Like if you take an asymmetric function in d variables, you permute it still.
Oh, you can only get d factorial different things there, right? So the thing is really.
That is small. So d is sort of.
Yes, yeah, right. So actually I should say k is small, like k is like n over 2 or something much smaller. So we're looking at relaxations of size n to the k roughly, and we're looking at, we're asking, we're essentially looking at, think of k as much smaller than n over 2, let's say n over 10, right? So then it does, this is a, so why is this theorem true? Well, this theorem follows from a theorem in group theory, which is essentially that if you look at the permutation group and you look at any large subgroup of the permutation group, so if you have a subgroup H of the permutation group, okay, such that H has size more than n factorial divided by n choose d. Right. So it's basically a really large subgroup. Then what could H be? It could be, for instance, all permutations that fix d variables, right? That's what you'd expect. You'd expect that H is all permutations that fix d variables. It's essentially something like that in the sense that H contains all even permutations that fix d variables. So there's a subgroup of H which is all even permutations of that fixed d variables. So you use that on the automorphism group of the function f, and you derive this theorem. Okay. Sorry, I rushed through that proof. I wasn't planning on doing that proof, but that's the reason I rushed through it. But yeah, okay. So in the yeah, okay. So now that we have this very powerful hammer, that if you take any function, the only functions that you can pick in a symmetric extend formulation are things like this that depend on a junta and summation xi. Now we will prove that prove a lower bound for symmetric extend formulations. Okay, our starting point is going to be an integrality gap for Shirley-Adams. The reason being, we want to prove a lower bound against functions that look like juntas, right? They're just a little bit more complicated than juntas. So let's start with some lower bound for juntas. So what does it mean to be a lower bound for juntas? So let's fix some function which Shirley-Adams cannot certify non-negativity of. And this is one of the very simple functions that you can use. So here's the function. If you look at, you pick an odd number m, okay, and you look at this function. Okay, I claim that this function is non-negative over the hypercube because summation xi, since m is odd, m over 2 is a fraction, is not an integer. So therefore, summation xi will never be equal to m over 2. It will be off from m over 2 by at least a half. So therefore, summation xi minus m over 2 whole squared is at least a quarter always. So this is a function and which is non-negative over the hypercube. Okay, and this comes from essentially knapsack problem. Basically, you can take any other problem that you like. For instance, you could take max cut, pick an integrality gap instance for max cut for Shirley-Adams, and that gives you a function which is of this form. Okay, meaning it cannot be expressed as a non-negative combination of non-negative juntas. Okay, so now we want to prove a lower bound against this more general class of functions. So it's going to be a little bit of cheating. So
what is the relationship between m and d here?
M and d. So so here actually d can be as large as m over 2. You need up to m over 2 rounds to certify this, but for the proof you could think of it as you want to prove an n to the d lower bound, and so you pick an integrality gap instance for d round Shirley-Adams. Maybe it's a max cut instance, which means you might have like 10 d vertices or something, and then you run the proof. Okay, so now we want to prove lower bound for this general class of functions. So let's fix n to be 2 times m. Okay, so we'll prove lower bound for correlation polytope on n vertices. So what do we want to prove? We want to prove that phi of x is not in the cone of functions of the form h of x sub j comma summation xi, things that are juntas and summation xi for j smaller than d or something, right? J smaller than d. Basically, we want to show that phi of x is not in the cone of these functions for small j. Okay, and that will imply the lower bound on the symmetric extend formulation. So suppose not. Suppose phi is in the cone, right? So phi is actually in the cone. So let's say phi of x is equal to sum of a bunch of functions of this type. Does it make so I'm assuming for contradiction phi is in the cone generated by functions of this type. So phi can be written as a non-negative combination of functions of this type. So lambda sub h are non-negative numbers. All right. Okay. So I did a slight cheap. I mean, I didn't give you all the details here. So first thing I didn't tell you is what is relation, how is m and n related? So n is 2m. So phi was a function on m bits. So you're saying phi is a function n bits. So how is that? So I'm thinking of phi as a function. So it's a function on n bits, but it's the same as applying this on the first n over 2 of them, right? So n over 2 it's just since n is 2m, phi takes only m inputs, you use the first half of your string as inputs to your problem. Okay, but this identity is still over x1 through x. Right? This is an identity over 0, 1 to the n. Right? Because we are talking about functions on 0, 1 to the n. This is a function 0, 1 to the n, and it's fine. Okay, so now the little trick is we just want to somehow eliminate this summation xi, because if we could eliminate summation xi, then we'll say phi is a combination of juntas, which would be a contradiction. And the little trick is you just apply a substitution here. So imagine setting x, the second half of your x1 through xn as the complement of the first half. So you set x m plus 1 to be equal to 1 minus x1, x m plus 2 is equal to 1 minus x2, xn is equal to 1 minus xm. Okay. Just the second half is the complement of the first half. You just substitute that here. The reason to do that is if I do that, summation xi is always m. If I take the string and its complement, the sum of all the bits is always m. So once I do that substitution, what happens to this identity? I get phi of x1 through xm is actually sum lambda h of x sub j comma m, like a fixed number. Now this is a junta, right? Because I eliminated summation xi. This is a junta. So I have expressed my original function phi as a non-negative combination of juntas, which is a contradiction because phi was an integrality gap instance for Shirley-Adams.
That part of where integrality gap, why is that particular inequality?
Right, sorry, it's not, right, so it's not very important what this form of the inequality is. All I'm saying is pick an integrality gap instance on m variables, like a graph on m variables. Okay. Now look at the fix n is equal to 2m. Now introduce, so that gives you m other vertices which are sort of isolated, just because the same function is if it's a graph, you have the graph and then you have n isolated vertices, and then its identity is still true. On that 2m size graph, you know that this identity is true. What that implies is this identity is true for any fixing of the dummy bits. So I may as well fix the dummy bits to the complement of the original bits and see what happens to this identity. It becomes an identity of this form, where if we have written the original hard instance for Shirley-Adams as a non-negative combination of juntas.
So that would be the objective function certificate.
Exactly. Yes. Yeah. So yes. Yeah. So this is the objective the function that's hard to certify in Shirley-Adams. Yes.
If one would restate this result, you're saying you're taking an integrality gap for Shirley-Adams and using it to prove a lower bound on the overall extension of life.
Yes, exactly. Yeah, you can take an integrality gap instance for Shirley-Adams, and that implies a lower bound for symmetric extended formulation of the correlation polytope. As you can see, the proof is a little bit of it's just a little bit of trickery. Having an integrality gap instance of Shirley-Adams gets you almost all the way to the end because it tells you it's not a combination of juntas. Then you have to deal with summation xi, then use a little trick to deal with it. And this is indeed the case that because of this lemma, symmetric extended formulations are essentially Shirley-Adams, but if you have to be more precise, I think theta bodies are probably sort of the correct term that essentially capture symmetric extended formulation. In the following sense, they capture every symmetric extended formulation is subsumed by Shirley-Adams. That's what I mean. If you take any symmetric extended formulation of size n to the d, it is the polytope is essentially subsumed by Shirley-Adams polytope of d rounds, in the sense that in every direction, the face of the Shirley-Adams is inside the polytope. So it's strictly better on every instance. That's the. Yes.
So how much were you using about the correlation polytope?
Not much. The thing that we really sort of use is that the underlying solution space, this 0, 1 to the n, is a product space. So we can talk about juntas and things like that. If you, for instance, talk about the matching polytope or the TSP polytope, the solution space is the space of all matchings. So now we are dealing with functions on matchings. And so it's a little bit more tricky to define juntas and so on, but essentially the key lemma is true, and essentially the following fact is true, that Shirley-Adams or the theta body actually captures any symmetric extended formulation, and the proof is essentially using the same technique. Just that, so in this case, the analysis is works very smoothly, whether it's in 0, 1 to the n or over matchings or TSP tours. In what we'll see next, which is the asymmetric extended formulations, we use Fourier analysis on 0, 1 to the n and so on. And you could hope that those techniques, you could have hoped that those techniques give you a lower bound for matching polytope also. But it's once you want to deal with functions on matchings, the Fourier analysis gets really hairy and it doesn't work out. But we don't know how to make it work. But yeah, so the functions that we deal with are functions on solutions. So it's the solution space.
So out here, you would be using symmetric functions on the symmetric group.
Oh, for the matching polytope?
Yeah, why is it simpler here in the asymmetric case?
Basically because of this key lemma, everything is really simple. If I tell you a function has a small orbit, you can essentially tell me what the function looks like over 0, 1 to the n. It's also similarly true for the matching polytope. But in a general relaxation, we won't have this crutch that we won't know. Yeah. Okay, I think it's a good time to stop. In the next lecture, we'll talk about asymmetric extended formulations.
Any further questions?
Where does the name Kunta come from?
It comes from, I think, elections, like theory of elections. What is it? Social choice, theory of social choice.
Okay.
Really, a junta is like a small set of people who decide everything, right?
Any other questions? Let's thank Prasad.